Okay, great. So let's get started with the next talk. And the next talk is Bootstrapping Quantum Extremal Surfaces by Alex. Please start.
Thanks a lot. So let me start by thanking the organizers for inviting me and for setting up this wonderful conference. I've had a lot of fun this week, learned a lot of interesting things. Also learned some hard to swallow things, like the fact that Switzerland has not been Germany in official football game since 1938. But in any case, it's been very instructive. So today I'm going to tell you about some recent work that I'm really excited about. The talk's mostly going to be based on this paper from early in the summer with Sean Colin Elrin, who is really an excellent grad student at UC Davis, and he's applying for postdocs this year. So look out for his application. But really, it's part of a larger program that we started a few years ago. So I'll also mention some older work with Nabil Iqbal, Sagar Lakande, and Yorit Krudov. So like we heard from Sean on Monday, the 21st century is really going to be all about quantum information. And certainly to understand quantum gravity, we really made a lot of progress thanks to quantum information since the beginning of the century. And really the star player in this whole program is the RioAggie Formula, or its quantum generalizations. And I'm sure you've all heard about this formula before, but just so we're all on the same page, let me tell you how it works. It's a formula to compute entanglement entropy of subregions of CFTs. And what you're supposed to do is you're supposed to, so here's a cartoon for this. The CFT lives on this black circle here. And we want to understand what the entanglement entropy of some subregion A is. And what you have to do is you have to find some surface that extends into the bulk. These are these couple of different red curves here. And you look at the area of this curve over 4 times Newton's constant. And you add to that the entanglement entropy, this time of the bulk fields that propagate on the space-time. So you could have gravitons or scalar fields or gauge fields. And you compute this quantity for arbitrary surfaces. And you look for the extremal one. And the extremal one is called the quantum extremal surface. And then the value of this functional on the surface gives you the CFT entanglement entropy. Okay, so this has really been the star player in this program. And this formula, you can derive it just thanks to the semi-classical gravitational Euclidean path integral using the replica trick. And this was first done by Lefkovich and Maldacena, and I'm not going to review it here today, but basically what you do is you do the replica trick on the boundary, you extend that into the bulk, you look for a smooth solution, and then you take the limit n goes to 1, and you work a little bit, and you produce this formula that I had on the previous page. Okay, and the new insight, the progress that we've made over the last 2 or 3 years is that somehow just using this formula is enough to produce a unitary page curve. So, you know, if you form a black hole and let it evaporate, you know, several decades ago, Hawking did that computation and showed that if you compute the entropy of the radiation, it just grows and grows and grows and grows and grows beyond bounds. And that violates the unitarity of quantum mechanics because it seems like you don't get back a pure state at very late times. And the new progress is that if you just take this formula that I showed you on the previous place, apply it, what you find is a so-called island, and that makes the entropy of the radiation go down and is compatible with unitarity at very late times. Okay, so what do we conclude from this? Well, we conclude that we can see avatars of unitarity just from semi-classics, right? This formula was derived just from the Euclidean path integral, and is enough to give us signs of unitarity. It's not, we haven't proven full unitarity because that would require proving unitarity of the S matrix, but at least we can see avatars of it. Okay, and there's, in this story, there was no need for any of the microscopic details, strings, brains, or anything like that. We just got it from semi-classics. Okay, and this is both remarkable and puzzling at the same time. It's remarkable because you get it from semi-classics, but it's puzzling because, you know, as string theorists, we might have thought, well, okay, ADS-CFT surely resolves the information paradox, but it will do that from the full UV microscopic theory, which is the conformal field theory, which contains all the strings and the brains, etc. Okay, so this sort of raises 2 questions immediately. Somehow, if the full microscopic details are not needed to see this unitarity, exactly how much of the conformal field theory do we really need? And say we manage to answer that question and understand sort of the part of the CFT that's needed for this purpose, you can then ask, well, how do these microscopic, or the part of the microscopic CFT data do you need? How does it get reorganized into this generalized entropy, into this RioAggie formula? Okay, so here's how you should think about this. There's there's some black box, which is called the Euclidean semi-classical path integral of gravity. This black box produces the RT formula for you. You apply the RT formula and you see unitarity. Okay, but to answer these two questions, you sort of need to go and deconstruct what this black box is. Okay, so the goal that what I want to do today is I want to present a dictionary between the microscopic data of the conformal field theory. So that's a list of operator scaling dimensions and their OPE coefficients. And the quantum extremal surface formula, the generalized entropy, which is an area term, and the bulk entanglement entropy. How do these microscopic building blocks get reshuffled and geometrized into this formula on the right-hand side? Now, ideally, I'd like to be able to do that for you in some higher energy process, which is like the formation and then evaporation of a black hole, but that's maybe too ambitious. So what I'll do today is I'll restrict to the low energy sector, to the perturbative sector. And in that case, this first question here, we know exactly all the operators that are there. We know exactly what their scaling dimensions are and what their OPE coefficients are. So the first part of the question is answered, and then the question is, how do they get reorganized? And this is a setup where we can really try to make this dictionary, sharp or precise. Okay. But before I tell you about this dictionary, there's some subtleties to keep in mind that people often bring up. The first one is that the entanglement entropy in a CFT, just like in any continuous quantum field theory, is UV divergent. And this comes from the fact that there's modes that are highly entangled, very close to the entangling surface. And so if you try to compute the entanglement entropy in the continuum limit, you get infinity. This is not a serious problem. We've known this for a very long time. There's many ways to deal with it. The most common ways is just to consider a different quantity, not just sort of the raw entanglement entropy, but maybe the difference of entanglement entropies between an excited state in the vacuum, or something more fancy like a relative entropy that has nice monotonicity properties, or mutual informations. There's many other quantities that probe what you want to probe, but that are UV finite. Okay, so this is not an issue, and I won't worry about it too much today. I'll just consider one of these quantities essentially. There's another issue which is much more serious and much more subtle, is that there's bulk UV divergences. Okay, when we compute, I told you this formula has two terms. It has an area piece, but there's also a bulk entanglement entropy piece. And just like in the CFT, when you compute entanglement entropy through this extremal surface, you get UV divergences, this time in the bulk. And that's much more subtle because there's no room in the CFT to see any sign of a bulk UV divergence. A bulk UV divergence doesn't really have a sharp meaning in the CFT. And the general lore, which has been checked explicitly in some cases, is that really, the divergence that you get from the bulk entanglement entropy should be renormalized into the quantum Newton's constant. Okay, Newton's constant, this is an interacting theory. There's loops, Newton's constant runs. And really the divergence that you see here should be absorbed into Newton's constant, okay? And then running the bulk RG is just shifting contributions from this bulk entanglement entropy terms into the area, or vice versa, depending which way you go. Okay, and also it's also known that there's field redefinitions in some cases that can also shift terms from one side to the other. But this immediately should tell you that maybe there's a problem with what I'm trying to do. I'm trying to give you a dictionary, between definite CFT microscopic pieces into this formula, but I just told you that what you call A and what you call S bulk might not be well defined. You can just shuffle it around by moving by doing RG in the bulk, or by doing field redefinitions. And maybe part of the surprise of what I'll show you today is that in fact we seem to be able to identify definite pieces that go into the area term and that go into the bulk entanglement entropy. Okay, so what does the dictionary look like? So like I told you, I'm going to consider the low energy part, or the perturbative part of the spectrum of the conformal field theory, and I'll say more about the setup shortly, but I'll consider just a low energy operator of low scaling dimension that acts on the vacuum. That's going to be my state. And then the relevant operators and their OPE coefficients, we know exactly what they are. It's just the operator that you use to create the state. There's a stress tensor in any 2D CFT, and then there's also multi-trace operators made out of these single trace operators. There's an infinite family of them, and they have well-known scaling dimensions at infinite n, or at infinite c here. I'll be in ADS3 CFT2 in just a second, but they also have anomalous dimensions. They pick up corrections at finite c, And so there's a first order correction here, and similarly for the OPE coefficients, there's sort of the generalized free field piece, and then there's 1/c corrections to that. So what does the dictionary look like? This is what the dictionary looks like. At leading order, so the leading order will be C to the 0 in the calculation I'll show today. In the CFT, you can exchange two types of operators. There's just the identity exchange, and then there's the exchange of all the multi-trace operators. And then this identity piece is completely captured by the area operator part, the A over 4G part. And then all the double trace operators, they go into the bulk entanglement entropy piece. And as I'll show you shortly, it's a little bit more subtle. There's sort of cancellations between the two, but I'll get back to that later. And this was already understood in this paper that we wrote with Nabil and Sagar a few years ago. This order is sort of testing the FLM formula, but it's not really testing quantum extremality. In the setup here at this order, the extremal surface doesn't move around. So if you really want to see the surface move and probe really what quantum extremality is, you have to go to the next order. And that's what we did in this recent paper. And we don't have a complete understanding of how things work, but we have a partial understanding. And at this order, there's also the identity exchange, and this time there's a stress tensor exchange. And what I'll show today, I'll just focus on this first box here. I'll show that that's fully captured by the area piece. Okay, and then there's a question of what happens to the anomalous dimensions, and then the change in the OPE coefficients of these multi-trace operators. And for now, this is question marks. And there's also question marks related to how cancellations will work at this order. And there's something else that's very interesting that I won't talk at all about today, but I'll mention it because it should be embedded in this larger program, is to understand what 1/delta gap corrections do to the setup. So from the gravity side, 1/delta gap corrections are like string theory effects. And here there's a context where you can probe directly what they're supposed to do in the CFT and then understand what their meaning in the bulk side is. And understanding what entanglement means in string theory, which is non-local, is still very much an open question. And this is a setup where you hope you can track that. But as I said, I think this is more like a future question. I just wanted to put it in this table here, since it's part of the larger program. Okay, very good. So this is sort of the main thing that I would want to convince you in the talk. And this was my introduction. And the plan for the rest of the talk is pretty simple. I'll dive into the details. I'll just try to convince you that this chart that I showed you is correct. And I'll first perform the CFT computation and then go on to the gravity computation and show you that they agree with one another. And I'll just finish with some conclusion and open questions. Okay, so let's get started. Like I said, for simplicity, I'll consider ADS3 CFT2. For everything that I say on the CFT side, it's not particularly relevant. You could easily generalize it to higher dimensions. For the bulk story, it's much more subtle, and I'll say a bit more about that at the very end. But for everything that I'm going to say now, we could easily generalize, but let's just do it in 2 dimensions for simplicity. So like I said, the state that I want to consider is a primary state where you act with a primary operator, which is single trace. You just insert it at the origin and act on the vacuum. And again, for simplicity, let's just make this operator scalar. And then I'm going to take my 2D CFT to live on a spatial circle of size 2 pi. And then my region A is just going to be a subset of the circle parameterized by some angle theta. And then as Alcaraz and collaborators showed a long time ago, there's a very nice formula for the Renier, there's a very nice formula for the Renier entropies of this excited state, or more for the difference of Renier entropies of this excited state, and it's given by some kinematical factors times a 2 endpoint correlation function of local operators on the complex plane. And the kinematics is as follows. The operators are grouped together in pairs. Here I drew like S4, so there's 4 pairs. And they're all the operators are on the unit circle. And the distance, the angular distance between the operators is theta over n between the different pairs. Okay. And so this is a very nice setup because, like I told you, I wanted to get some mapping between entanglements and the microscopic CFT data. But here, entanglement and entropy, or for now, Renier entropy, is computed by a local correlation function. And a local correlation function is exactly what we know how to massage and extract all the CFT data from. Okay, so it gives us a bridge between when we're going to look at the bulk dual, it's going to involve the RioAggie formula, but on the CFT side, it's a local correlation function, so we can extract the CFT data from it. Okay, so this is a formula that's true in all 2D CFTs, but in general, it's very hard to compute because it's a 2-endpoint function. But for holographic theories at large C, it's easier because these operators are basically generalized free fields plus 1/C corrections. So at leading order in the large C expansion, we just have generalized free fields, and then this correlation function would just be given by all the possible Wick contractions between the operators. And so for any given n, it's completely possible to compute just this correlation function. It's easy. You can do it, on 2 lines in Mathematica. But for a generic conformal dimension, it's still very hard to analytically continue that in n to n goes to 1, which is what you want to extract the entanglement entropy. So we can't quite do that for generic scaling dimension. So what we do instead is we take the small interval limit when this interval size theta becomes small. This is the limit where the pairs of operators are coming together. So all the operators are coming together pairwise, which is an OPE limit. And then what you can do is you can expand the correlation function in this OPE limit and analytically continue the terms in the OP expansion term by term. Okay, so that's what we do in practice to deal with the analytic continuation. So at order C to the 0, like I said, this is the order where you just have generalized free fields. It's very easy. There's just 2 contributions. I mean, there's many more in the OP expansion, but the 2 first contributions that appear are easy. The first one is just the identity operator. So, 2 of these O's can fuse to give you the identity. And 2 of these O's can also fuse to give you a double trace operator, which is this term here. And once you do the analytic continuation, this is what you get. Okay. At order 1/C, it becomes more complicated. There's 4 types of possible contributions that you have to track. The first one is a bit non-standard from a large N bootstrap perspective, and I'll come back to it later in the bulk side. But in principle, the scaling dimension of the operator O may have itself a 1/C correction. So there could be an anomalous dimension to the single trace scaling dimension itself, and that would give you a contribution at order 1/C. There's now a new operator that you can exchange, which is the stress tensor. And say in 2D, there's both T and T bar. And then, as I told you, the multi-trace operators, they pick up anomalous dimensions. So you have to also correct by the change in the single trace dimension, but they pick up an anomalous dimension. And similarly, the OPE coefficients change. Okay. But what's important to note is that this anomalous dimension and change in the OPE coefficient, they're completely fixed by crossing. Okay. If you assume that the only operator that you can exchange is the stress tensor, and say we're going to take our bulk theory to be just a free field minimally coupled to gravity, so there's no quartic couplings, then these 2 numbers here are completely fixed by crossing symmetry. Okay, and we know exactly what they are. There's very simple expressions. I'll show you in a second, and this was worked out in a paper by Collier et al. On the other hand, the change in the single trace scaling dimension is not fixed by crossing, at least not perturbatively. And so that will be important to keep in mind for later on. Okay, so those are all the 4 contributions, and you just work out the details, and this is what you get. This first term here is the exchange of the identity, which basically just gives you the anomalous dimension of the single trace operator. This second term here is the exchange of the stress tensor. This second and third line here, which is a bit of a messy expression, is the anomalous dimension to the double trace operator. And this last line is the change in the OPE coefficient of the double trace operator. Now, like I told you, these things are just known explicitly. They're simple functions like h² / c with some number up front. Okay, and like I said, in this talk today, I'm not going to give you the full dictionary. We're still working on it. I just wanted to focus on this first line, which was just the identity and the stress tensor exchange. And so that's this first line here. Okay, and what we're going to try to do is understand where does this come from in this quantum RT formula. Okay, and you might wonder how am I even separating this first line from the rest? And there's an easy way to do that. You just look at the theta dependence. This contains only even powers of theta, whereas the other terms scale like theta to the h or theta to the 8h, and so you can separate them meaningfully. Okay, good. So this was the CFT computation, and now I'll turn to the bulk side of the story. So the first thing that I need to do is tell you what the bulk state is. So I said that in the CFT, our state is given by a single trace operator acting on the vacuum. On the bulk, what that means is that there's a field phi that's dual to this operator O. You can expand this field in modes, and then the bulk state that's dual to the single trace operator acting on the vacuum is just the lowest mode of this field acting on the bulk vacuum. Okay, it's a 1 particle state of the bulk theory. And at first order, at order C to the 0 or G un to the 0, the bulk theory is sort of simple. It's just free fields propagating on an ADS background. And there's two effects that will touch the RT formula. The first one is that the geometry changes. Once you're in the one particle state, you can compute the expectation value of the bulk stress tensor. And it looks like this. Here's the TT component of it. There's basically some lump of matter sitting at the center of ADS. And how wide it is depends on the mass of the particle. It's like the Compton wavelength. So it's inversely proportional to H. And so because now there's a non-trivial bulk stress tensor, you have to go back and solve Einstein's equation. Okay, so you have to go solve the perturbative Einstein's equations. You expand the metric around ADS with a small correction. Turns out it's a very simple solution to Einstein's equations, and you should think about it as a regularized conical defect. If you look at the solution from very far away near the boundary, it looks like a conical defect, but when you zoom in, the conical defect is regularized, if you want, by the Compton wavelength of the particle. So it's a completely smooth solution. That's pretty nice. Okay. And I should mention that at this order, you don't need to look at the change in the surface because the surface was classically extremal. If you do a small metric perturbation, you don't need to worry about the surface moving at this order. Okay, so that's one effect. You can go and compute the change in the geometry and then compute the change in the area. The second effect is that the bulk entanglement entropy gets polarized by this new state. Okay, and the easiest way to see this is the following, is that the one particle, so this is the creation operator in global coordinates in ADS, but you can do a Bogoliubov transformation and rewrite it in terms of Rindler modes, B and B dagger. And what you've all heard is that the vacuum of, say, a quantum field theory on flat space, if you trace over the left Rindler wedge, you get a thermal state on the right Rindler wedge. The same is true in ADS. There's ADS Rindler coordinates. You can trace over one of the wedges and get a thermal state. But now we're no longer supposed to consider just a vacuum. We've acted with some operator on the vacuum, but you just rewrite that in terms of Rindler modes. And so what this looks like is like a small perturbation. You'll get no longer the thermal density matrix in Rindler, but you'll have small off-diagonal components. So it's a small perturbation of the Rindler state. And you can go ahead. You have an explicit expression for the states. We have to compute the Bogoliubov coefficients with Nabil and Sagar. We did it. You have an explicit expression for the state, and you can go and compute the bulk entanglement entropy. And at this order, if you compute the difference of bulk entanglement entropy between the excited state and the vacuum, it's bulk UV finite. So you see no subtlety in terms of bulk UV divergences here. Okay, so putting all these pieces together, what do you get? The area term has two pieces. It has this first line here. Then there's another piece that goes like theta to the 4h, and then you compute the bulk entanglement entropy. It also has two pieces. And again, this is plus ... We're always doing a small theta expansion. And you see that there's two pieces that cancel exactly against one another, and you may not remember, but this is exactly the answer. These two pieces that remain is exactly the answer that I showed you from the CFT. Okay, so you exactly match the CFT answer. And remember, the first term here, this was the identity exchange, and this was the double trace exchange. So here it seems that at this order, in the area term, there's just the identity operator, and in the bulk entanglement entropy, there's the double trace operator. And there's this extra subtlety that there's a piece that appears at the intermediate stage of the calculation that seems to cancel in the bulk. Okay, and it had to cancel because it scales like theta to the 4h, and there was no term in the CFT that scales that way. Okay, so this is some interesting things that happens, and I'll come back to it at the very end. But modulo these cancellations, you can identify which operator contributes to which term and completely match the CFT answer. Question? Yeah.
Actually, two questions. I mean, of course, whatever the answer was, as long as it added up to be right, you could have said it was the first term matched the identity plus a correction that canceled the correction on the other side, right? I mean, and I guess what I had in mind is, if somebody gave you this formula and they didn't tell you the CFT answer, for example, or vice versa, would you be able to have figured out that the correction, you know what I mean?
Well, so in this setup, you can compute A without computing S bulk, and you find this first line here.
Right.
That's fine.
That's fine.
You compute the second line, you find this thing here, and you add them up, and then you get the CFT answer. But you can sort of, you can, this term here, actually in both computation, this term is really meaningful. It's something that you see has nothing to do with the bulk UV divergence. It's just a piece that's there. You can ask, what does it mean in the CFT? Yeah.
Is there something subtle in this context about that? I mean, the quantum state that backreacted to make this change in the area, it really looked more like a particle with an uncertain position given by that wave packet. And so in principle, the backreacted geometry is more like a localized conical singularity whose location is a bit uncertain. And so the metric you have is like the smeared version. But so for computing the area, that doesn't matter because the linearized order and the perturbation, it doesn't matter for the area, of course. But could that have anything to do with this term, do you think? Or?
Yeah. So this term, actually, you can understand what it is or where it comes from. It's like the expectation value of the bulk modular Hamiltonian in the bulk one particle state. That's what gives you this.
Okay, thanks.
Okay.
I have a somewhat related question. So
Yes.
you indicated at the beginning that there is the separation between A piece and the bulk piece could depend on the energy scale, etc., RG related issues, etc. So in this comparison between CFT and the bulk, are you sure that you're using the same scale?
Yeah, thanks. That's a great question. So let me say it again, is that here you could have worried about this, but it just so happens that when we look at the difference of states, so that's UV finite in the CFT, but it also happens to be UV finite in the bulk. So the energy scale disappears from this problem. If you had looked at any of these two terms independently, you would have been confronted with this.
Okay, thank you.
Yeah. Good. Okay. Great. So let me tell you what happens at order G Newton. And I think this is where things get murky. What we mean by semi-classical gravity at this order, I mean, I guess Daniel already asked a question related to that about what's the interpretation of the one particle state. But at this order, things get really murky. Scalar field interacts with gravity. And you have to be careful that what you're doing is correct. We did something that makes sense and seemed to match the CFT answer, but things get more subtle. So I'll tell you what we did, and then we can discuss if it was the right thing or not. Okay, so once you go to this order, at least we know in principle what you're supposed to do. You take the ADS metric, and now you expand it not just to first order, but also to second order. And similarly, you take the location of the extremal surface. It was the classical extremal surface on ADS, and you expand it to first and to second order. Okay, and then what we want to do today is just look at the contribution of the area term at order G Newton, and there's a bunch of different contributions that could appear. The first one is, say, given by the 0th order surface, but on the first order metric squared. Then there's like, then there's the 0th order metric on the location of the surface squared. So there's like this term squared, then there's like a cross term, and then there's a term coming from the second order change in the metric and on the 0th order surface. And in principle, there could have been a final term, which is the second order change of the surface on the 0th order metric. But again, by extremality, you can drop this term for the same reason that we could drop this term at first order. Okay. So the first term here, we know how to compute. It's just, it depends on just this metric G1 that we already had in the previous case. But there's two new pieces that we need to find. The first piece we need to find is the second order backreacted metric. And then we also need to find the first order move in the surface. Okay. So that's what I'll try to do. And let me start with the second order change in the metric. So remember, the way we got the first order change is that we solved the scalar field wave equation on ADS. We looked at the one particle state that produced a stress tensor for us. Then we backreacted that stress tensor onto the metric. So here, what we're supposed to do in principle is well defined. We're supposed to solve the wave equation, this time no longer on the ADS background, but on this, on this backreacted background at first order, solve the wave equation here, expand it in modes, and then look at the one particle wave function and backreact that. I mean, compute the stress tensor and then backreact that on geometry. Okay, and it turns out that this geometry is simple enough that you can solve the wave function analytically. It's a bit complicated. It's like a hypergeometric 3f2 function or something. So I'm not going to write it explicit here, but you get just the ADS wave function that's very simple plus a correction that's some complicated hypergeometric function. And maybe just It's interesting to note that if you expand this near the boundary, what does it look like? Well, it goes like 1 over r to the delta. That's the expected thing that we all learned from ADS CFT. Plus it has a correction proportional to G nu that's given by 1 over r to the 3 delta. Okay, and you can understand where that comes from. It's because, you know, the first order stress tensor behaves like 1 over r to the 4 delta near the boundary because it's quadratic in phi. So it's kind of natural that you get a structure like this. Okay, and then to find the second order metric, we do the same thing as before. We, we compute the expectation value of the first order stress tensor and back react it on the metric. Okay, and this is, you can solve for this. I mean, this is really where Sean was really brave. It's, if already the wave function was complicated, the expression for the metric is even more complicated, but you can still solve it analytically. And so we have the solution to the equations of motion at second order. And again, you should interpret this, as a conical defect, but that's regularized and gravitationally dressed to second order. But again, I want to emphasize this is a smooth metric everywhere, right? Smooth at the center. Okay, and once you find this metric, you go ahead and compute the piece proportional to G2. Okay. But before I move on to tell you what happens to the change in the surface, there's something a bit funny that happens here, and you can ask, what's the energy of our state? Okay, and the energy of the state, you can say compute it from the second order back-reacted solution by looking at the ADM mass. And what you find is there's a leading order contribution, which is just 2h or delta. That was the weight of the primary operator. But there's a genuine correction or a 1 over c correction given by this formula here. Okay. And so if you go back to the CFT and look at the energy of the state in the CFT and wanted to claim that it's just delta and doesn't get affected at order 1 over c, you seem to see a mismatch. Okay, because in the CFT, if I remove this second term here, then the energy of the two states don't match. So we haven't identified the state correctly. But okay, maybe you say that's not a problem. I just add this anomalous dimension to the single trace operator, and then I should be good to go. But this is still problematic because remember I told you that the anomalous dimension of the single trace operator is a free parameter. In the CFT, I can tell you whatever it is. I can make it pi over c, like it's my freedom. It's not fixed by the bootstrap in any way. And if I make it pi over c, it's obviously not going to match with what I computed from sort of self-gravitation in the bulk. So how do you make sense of this? And there's one more thing that we could do that we didn't do, is that we can also make a perturbative change in the mass. Okay, we could have changed the mass by a little bit, and that also affects delta H. So really the way that you're supposed to think about this is that, there's a self-gravitating energy in the bulk, and there's also a change in the mass. And really the only thing that the CFT has access to is the sum over the two. So what we're supposed to do is we're supposed to agree on this first. You tell me what you want this thing to be, and what I'll do is I'll tune the change in the mass accordingly, and then such that when you add the self-gravitating energy to it, it'll match what the CFT answer is. Okay, so we got confused by this for a long time, and people don't talk about anomalous dimensions of single trace operators too much, but this is how we think about it. And of course, non-perturbatively in the bootstrap, this is supposed to be fixed. And maybe for a BPS operator, it's even supposed to be fixed to 0. But okay, so this is how we make sense of it here. And now, how am I doing with time? 5 minutes. 5 minutes. It should work-ish. So now, how do we find the location of the surface? And the easiest way to do that is to go to Rindler coordinates in ADS. So here's the ADS Rindler metric. It covers the red region of the geometry here. And remember, there's also a first order correction to the metric that is very simple in global coordinates. It's very messy in Rindler coordinates. So I'm not writing it out explicitly, but it gets corrected here. And the nice thing of these coordinates is that the classical extremal surface is just the Rindler horizon, which is just rho equals 0. Okay, so then the quantum extremal surface will now move. It'll be 0 plus something proportional to G Newton, some first order shape deformation of the surface. Okay, so you can ask, what is the area functional as a functional of this shape deformation? It's given by the following expression here. And so you can go ahead and use that to compute. But remember, there's another piece. You're not supposed to extremize just the area. You have to extremize the area plus the bulk entanglement entropy. Okay, but like I said, a change in the location of the horizon is just basically what's known as a shape variation for entanglement entropy, and it's something that people have studied a lot. And so there's a formula for this. If you look at the functional of the bulk or of some entanglement entropy as a function of a shape variation, you can massage it to be given by basically an integral of this shape varying function times a 2-point function, of the stress tensor. This is the bulk stress tensor times the bulk modular Hamiltonian. Okay, and for a general state, this is a non-local operator. So this object can be in principle complicated, but it's given by the following formula. And when you put everything together, you work out what the equation of motion for the location of the surface is. It's a very simple equation of motion. It's just, it has a homogeneous piece that's trivial and that we could all solve in real time, just an exponential. And then there's two sort of inhomogeneous pieces. One comes from the fact that there's a first order change in the geometry. It's like a geometric force pulling on the surface. And the other will come from this entanglement entropy piece. And it'll also pull on the surface kind of independently. And we can't compute this. We're working on it. We're trying to compute this, but we already know how to estimate its order as a function of interval size, and it only goes like theta to the 4h. So like I said today, at this order, I only want to compute even powers in theta, so you can essentially drop this. Okay, and so the point is that because the form of the equation of motion, you can sort of deal with the two things independently, and you can consider a geometric move of the extremal surface. Okay, so that's what we'll do. We'll look at a shape variation that satisfies this equation. And this equation is ugly, but again, Sean was very brave. You can go and you find an analytic solution to the equation of motion. And so this is how the surface moves. Okay, x is the spatial direction along x, and it's some complicated hypergeometric function that tells you how the surface bends. Okay. And again, once you have this, you go, you put everything together. Now we really have all pieces that we need for A. We have gamma 1, we have G2. You put everything together. You go and you compute the area operator to order G Newton, and you get this answer here. Okay, and again, there's a lot of very complicated other terms. Even neglecting the bulk entanglement entropy piece, there's a lot of complicated other terms that I'm dropping here. But the even power expansion looks like this. And without loss of generality, we can just pick a scheme where the change in the bulk mass is 0, and then you'll recognize that what appears here is exactly the change in the single trace operator. Okay, and so you get this, which exactly matches the CFT answer. And so this is, the justification for the first line of the dictionary that I gave you at the beginning of the talk. So just to summarize, what I did today is I presented the first few steps of some dictionary that's supposed to, tell you how the microscopic CFT data gets reshuffled, repackaged, and geometrized into a quantum RioAggie formula and a quantum extremal surface. And if you want, you can view this as a partial check. It's partial because we didn't compute the bulk entanglement entropy yet of the quantum RT formula at second order, where quantum extremality is really important. And essentially nobody's done this yet. Of course, most of the calculations that involve quantum extremal surfaces really happen in two-dimensional bulk, where there's no surface to extremize, there's just a location of a point. So there's been computations, and that's how all this island story came about. But in higher dimensions, it's more complicated. And so we were able to do that at least partially here. And what we seem to find is that at least up to this order, the Virasoro identity block, which at this order is a bit trivial, it's just the identity plus the stress tensor, but it seems that at this order, that's completely captured by the area operator. Okay, we didn't need S bulk at all for these pieces, and we show that these pieces cannot appear in S bulk actually. Okay, so what's left to be done? Well, we have to compute S bulk. We're working on it. It's hard. For now, it's mostly technically hard because there's a lot of complicated integrals, but there's also some conceptual questions. But we're working towards this, and hopefully we can get these remaining two lines in the dictionary. And you can ask, what about boundary gravitons? So at this order, the gravitational field interacts with the scalar field. So why did we not take into account the entanglement entropy of the boundary gravitons? And we don't really know why we were not supposed to do it. We just didn't do it, and we got an answer that matches the CFT. And we don't think that boundary gravitons, we think if boundary gravitons were supposed to contribute, they would also contribute even powers in theta just because of the weight of the stress tensor. And they don't seem to be needed. We think that they're only relevant if you consider not a primary operator, but a Virasoro descendant of an operator. Then you polarize the entanglement pattern of the boundary gravitons. But okay, we don't know for sure. And then there's this question of bulk cancellations that we saw already appears at order C to the 0. And we don't know exactly the details of what happens at the next order yet, but we know there's going to be a ton of cancellation between pieces in the area operator and pieces in the bulk entanglement entropy. And again, we don't really know what we're supposed to do with these cancellations. Is it possible to extract these terms that cancel directly from the CFT? They don't appear in the answer that we compute here. Maybe they appear in something else, but we don't quite know. And of course, the question is, can we really distill how the microscopic building blocks move into S bulk or A over 4G, say to arbitrary orders. But okay, that's for the future. So let me stop here and thank you for your attention.
Okay, time for questions online, offline. Yes.
So this the CFT calculation is done for some generalized free field. Can you also do it in a symmetric orbifold? And can you see what really happens? I mean, aren't there terms where you can have single trace operators appearing at?
Yeah, that's going to be very hard because we picked a toy model where the gravity dual is just a free field, you know, a free scalar field minimally coupled to gravity. The problem is that in a true symmetric orbifold, let me go back. Where's the correlation function? In a true symmetric orbifold, two operators O can exchange a ton of other operators, right, on top of the stress tensor. So I think for a first cartoon for that would be, okay, let's also consider now another operator, O twiddle, and look at the contribution of O twiddle here, figure out the dictionary for that, and then try to resum that into all the operators that exchange in the symmetric orbifold. In principle, it's doable, but I think it's going to be some work. Yeah.
So you think that a dual gravitational description will be very complicated because you need lots of additional stuff there?
Yes, yes, and potentially, you know, an infinite tower, and then it becomes hard. Yeah.
Yes.
Yeah, so about this formula for the Renyi entropy, can you actually just match this formula to the bulk dual, the Dong formula for the Renyi entropy? And would that help in going beyond a small subsystem limit?
Yeah, thanks. That's also a great question. So in principle, yes. So by doing that, the difficulty that you avoid is that you don't have to do the analytic continuation. So in principle, you do it for arbitrary system size. The price you pay for that in the bulk is that you have to add a brane with non-zero tension. And that seems harder. We didn't try. It's worth trying, but so there's some kind of conservation of misery. That,
on the bulk side, it seems more complicated. But from the boundary, it might be.
Yeah, but the bulk side is already the hard part. So I'd rather try to make the bulk as easy as possible and keep, you know, I'd rather push all to the full extent the difficulty to the CFT, because at least there I know what I'm doing. So.
And another question about the cancellation in the bulk. So if you consider relative entropy, then does this term actually appear again as a?
Yeah, the same problem appears for relative entropy. The only difference, so remember relative entropy, the only difference in the boundary is that you also have to subtract the difference of the vacuum, sorry, you have to subtract the difference of the vacuum modular Hamiltonian in the excited state minus that in the vacuum. And that's exactly this term here. So the only difference is that this term drops, but we understand where this term comes from. And everything else to higher orders is completely the same.
So the cancellation in the bulk is still there.
It'll still be there. Yeah.
Joe?
Yeah, you mentioned, but let me insist. So is it clear that this is the right way to compute the second order? Because aren't you like neglecting some interference? Because if you have some quantum system, if both things were quantum, it should not be equivalent to just take the quantum average and then go to next order and then the next average, right? You're always computing the correction of the metric using averages of the stress tensor. So that works at first order, but I guess it should not work to all orders in perturbation theory, right?
Well, I think that's related to what Daniel was asking. Exactly. I think in principle I agree, but the question: what is the right prescription? Yeah. Right. So the way we're interpreting the expectation value, yeah. So I think what you're saying is that at next order, you know, in the area so now we think about the area operator as an operator. It has a metric in it, which is an operator. And when you expand it out, it doesn't have just 1-point functions. It has also like 2-point functions of the metric, right? And so somehow you have to take that into account. I think maybe here is another case where somehow we didn't seem to need this, and that's something that you might have worried already for the terms that I computed today. I think maybe that's due to 3D gravity, is that maybe in 3D gravity, you know, the metric part of the theory is topological. So, you know, all the degrees of freedom are shoved into the scalar field. Of course, you don't have to package it that way, but it's convenient to package it that way. And then maybe all these terms disappear. But I don't have a very sharp answer. That's kind of a, yeah.
Thank you.
That's kind of a guess.
Okay, there is time for, say, one more question. No? What about online? No? Oh, okay, yeah, sure.
And so what about higher curvature corrections in the bulk? So don't they mix at this second order with the corrections you considered already? I think that's what
So those are,
Emparan in his quantum BTZ black hole paper found.
yeah, I'd say in the standard setup, those are supposed to be here, right? That's about 1 over delta gap. And then there's this extra weird thing that we're in 3D gravity where higher derivative corrections don't really do much. Or in other words, you know, the 3-point function of the stress tensor is universal. You know, the stress tensor can never appear in the OPE of two scalar operators, unlike in higher dimensions. So it's going to be a bit different to diagnose what you mean by higher derivative corrections here. But you could still imagine the exchange of a heavy particle of spin 3. That gives you something in the CFD, and you ask, how is that captured in the bulk? And I don't know, but I don't think it. I mean, of course, you can take delta gap to be related to C in some way, in which case you can't disentangle anything, but you don't have to do that. I would say to build a dictionary, just make it a separate scale for now and treat those effects independently.
Okay, thank you. So I think the time is up. So let's thank Alex again.